Another word we could use.
Helper. Volunteer. What teach?
That's good.
Anyway. So it's been like 3 weeks since we started this PowerPoint. But we're going to be continuing on quartz. So how do we go with remembering details on quartz? We're going to do a little bit of a deep dive tonight because we're going to start talking about treatments of quartz. And although it's not examinable this year, I do want to do a small amount of time on synthetic quartz as well. And then we're going to finish the night by looking at cryptocrystalline quartz and things like agates and the more ornamental varieties. Where we got up to the last time, we were up to twinning. So we ended on this slide. Hey, that works. This is a fun little fact about quartz, but this particular slide is not examinable. But it's one of the things about quartz that students tend to remember, so it's a little bit fun. Quartz has a really cool electrical property called piezoelectricity. Has anyone heard of it? Nope. If you
Yes.
Better. So when you apply mechanical stress to a quartz crystal, when you squeeze it, it develops an electric charge and it begins to oscillate. It's this property of both quartz crystals which is exploited to run things like quartz watches. So we have mechanical watches that run on gears, but if you have a quartz watch, it runs on a little slither of quartz crystal, which is oscillating and keeping time of the seconds. Vice versa with quartz as well. If you apply an electrical charge to quartz, it will develop mechanical stress across opposite faces of a quartz crystal. So that is called piezoelectricity. It is also very, very slightly, has a small amount of pyroelectricity, which develops an electrical charge when it's heated. Tourmaline develops much stronger pyroelectricity. It can attract dust and clear out things like ash when you heat a tourmaline crystal, which is a really cool fun fact. 100 years ago, they used to use tourmaline crystals to clean out pipes, like smoking pipes. You used to take the ash out with a tourmaline crystal. Fun fact. We're going to go through different types of varieties of quartz. And so we're going to go through by color and just do a little bit of an explanation. So quartz is the family of the mineral, but each variety has a different name depending on what color it presents. So this should be run of the mill by now. The colorless variety of quartz we refer to as rock crystal. So on test sheets, when you're identifying a piece of colorless quartz, the correct notation is actually natural quartz variety rock crystal, if you're looking at a crystal of colorless quartz. Some of you on your mid-year exam might have seen that notation corrected for you to say we would appreciate you say variety rock crystal after the natural quartz. Little bit of trivia. Early Greeks thought that rock crystal or quartz was actually a type of water that had frozen so hard that it wouldn't melt. There is a type of quartz that you may be asked upon in exams. It is collectible for mineral collectors. It's called a Herkimer diamond. And a Herkimer diamond is a misnomer. Misnomer is when a name of another mineral is inappropriately used for the mineral that it actually is. So a Herkimer diamond is not actually a diamond. It is a quartz crystal. It's a doubly terminated quartz crystal that is usually relatively high quality in terms of the number of inclusions. It's usually very high quality inclusion free sample. And they usually have very, very sharp terminating faces at either end of the crystal, usually damage free. Herkimer diamonds come from one particular area in America where they're named after, which is Herkimer County. But any doubly terminated clear specimen of rock crystal, I'm just going to let that individual in, is usually referred to as as Herkimer diamond. From current slide. So these are examples of some little Herkimer diamond crystals. We do have some that are genuine from Herkimer County in the collection that are named Herkimer diamonds. And these are just examples of what they look like. Usually, very, very clean, very bright, doubly terminated crystals. These are the ones that we actually have in the collection, photographed on a background, because it's really hard to photograph colourless stones if you don't have them on a coloured background. So these are the ones that you see in the collection. This one here is an example of a doubly terminated rock crystal, and quite often they will be sold as Herkimer diamond, but these ones come from Pakistan, not from America. The reason I know they're from Pakistan is because of this yellowish greenish coloured liquid inside the crystal. From Pakistan, it's the only known locality that has this yellowish liquid. They have 3-phase inclusions. The yellowish liquid is a petroleum-based liquid, naturally occurring, and it is highly fluorescent. So get your UV light out and it really, really lights up. And they're really, really collectible because everyone loves a multi-phase inclusion and a moving gas bubble. You can even get these things faceted as well. They're lots of fun, but they are from Pakistan, not from Herkimer County. Moving on to amethysts. Another fun fact, the early Greeks believed that drinking from an amethyst cup would prevent intoxication. If anyone wants to give it a go, I'm not saying it will work, but you can buy amethyst cups.
We should have one.
We should have one, a communal amethyst cup to try out in prep class. I don't think so. Amethyst is the purple variety of quartz. Is someone wanting to ask a question online?
No, I'm just going to say that I am a February born Leo because of my time of birth. So
Yes.
amethyst is the February crystal and ruby is my firestone for Leo.
Yes.
So
Amethyst is the birthstone for February.
yeah, so it's my purple and red together. So amethyst is a crystal, but ruby is a whatever.
Yes. Yes. So moving on.
So my question is,
Yes.
I'm screwed. Thank you.
That's okay, Kavitha. Amethyst crystals are usually well formed. They frequently line cavities and geodes, which we're not going to go into because we haven't got enough time actually, but it's really, really fascinating to go into the formation of geodes. We're concentrating on identifying features of the quartz gemstones. So information that you need to know about amethyst. Natural amethyst, the color is banded or patchy. It is expected that the color will be banded or patchy. When they cut the amethyst, the cutter will orientate the material to make the face-up color, the color that we see through the crown, look as uniform as possible. But when we immerse it in liquid and look from the pavilion, we'll notice an uneven distribution of color. That is really, really important because that is one of the ways that we have of potentially separating natural material from synthetic material, which we'll be talking about later. The color of amethyst is due to these color centers, which we've touched on really, really briefly before. And it's a color center associated with iron. And it's from natural irradiation from adjacent rocks. This is a specimen that's in my collection. We've got a couple in the GAA collection here too, out of a parcel that I bought. This is a slice of quartz crystal that has been cut perpendicular to the optic axis. So the large face that you can see is perpendicular to the optic axis. What's really, really cool about this sample is you can see the zoned color of the amethyst crystal. So amethyst crystals, also with ametrine crystals, it doesn't always happen, but it's fairly common to have the color alternating under the minor and major rhombohedral faces. So we can get triangular zoned color within the quartzes. Color center, when we talk about color centers, it's a defect in the quartz structure and the crystal structure itself. The color center, the elements that cause color in a color center are associated with elements that don't usually cause color. In quartz, it's the oxygen atom that is associated with the cause of color in conjunction with the iron atom as well. So what we have is the natural irradiation from the surrounding rocks ejects an electron from orbit around one of the oxygen atoms. So oxygen has a pair of electrons, and it usually takes a larger amount of an energy to separate a pair of electrons. That irradiation is enough energy to send one of these electrons out of orbit from that oxygen atom. And then that electron wanders around a little bit through the crystal structure, looking for somewhere else to live. If it can't find anywhere else to live, it will return back to the oxygen atom. And if it returns back to the oxygen atom, then we don't have any color produced. But what often happens with quartz is that we can have these other defects in the crystal structure, and we can have atoms that are swapped out of the crystal lattice. This picture here that I took out of the Kurt Nassau's 17 causes of color. How many causes of color? Kurt Nassau's causes of color book. This is actually for smoky quartz, not for amethyst, but it illustrates the process. So we actually have in this diagram an aluminium atom substituting for where a silicon atom should be. In amethyst, this would be an iron atom rather than an aluminium atom. There is a difference in charge. There's a slight imbalance in the valency between the silicon and the aluminium, and that is balanced by having a hydrogen interstitial element. So we've got this tiny little hydrogen atom that sits nestled inside the crystal lattice, not actually bonding with any of the atoms around it. But that little hydrogen atom is wanting a single electron to fill its valence shell. So when the electron is ejected from orbit around the oxygen atom, then this little electron attaches itself to the hydrogen atom. Chocolate biscuits, energy. So the electron attaches itself to the hydrogen atom. So what that causes is a tiny little hole where the electron should be in orbit around the oxygen atom. And it also has another disturbance where we have this interstitial element of the hydrogen, which has trapped the electron from the oxygen. So we call it a hole. We have a hole center and a trap center. And that exchange, that movement of the electron is what causes the color in the quartz. So this is what a color center is. Quartz isn't the only gemstone to have color centers. When we get into Gem 2, there'll be discussions when we talk about treatments of how we can irradiate gemstone materials and which gemstone materials might respond to irradiation. Quartz is one of the materials that can be naturally irradiated within the Earth's crust, or we can irradiate it in laboratories. Stones such as topaz routinely undergo irradiation to change the color of the topaz. We can also irradiate other gemstone materials such as kunzite. And irradiation works because it creates color centers or it reverses color centers that are present. So we might want to reverse the process and release an electron that's been trapped and send it back home to where it used to be, or we might want to create a color center and open up one of those color holes that will then change the way the light interacts with the crystal and result in absorption where we wouldn't normally have absorption. So this is a color center. So we've got the electron color centers and the hole color centers. So the electron trap and the electron hole. In both cases, the color center is able to absorb only certain amounts of energy, and those certain amounts of energy are going to correspond to a particular color that is observed by the eye. For the color center to work, we need both the trap and the hole present. If there's no trap to keep the electron, then the electron's going to wander back and fill the hole that was created by the irradiation. With the irradiation, I mentioned that we can undo the effects of a color center. Heat and irradiation are considered two sides of the same coin. So frequently, if we create a color with irradiation, we can reverse that color or destroy the color by heating the material. With quartz, particularly with amethyst, if we heat amethyst to between 400 and 500 degrees Celsius, then it will no longer be purple. Instead, it becomes yellow and we call it citrine. It's estimated that up to 90 to 95% of the citrine that's commercially available on the market is the result of a heat treatment process from amethyst. And unfortunately, there is no way that we have, no tools or tests that we have to determine whether the citrine that we're selling has been heated or is unheated. There's no peaks in any spectra that's going to tell us, but we assume that the process, that it's gone through that process. We assume that the citrine has been heated and it's considered industry standard. If we want to reverse that color, we can irradiate the citrine and it will send it back to a purple color. But that process is expensive and you need to send it offshore, and they don't do individual stones. But they quote on parcels in kilograms to do that. We have to be a little bit careful with quartz. Quartz, we can induce thermal shock. And when we induce thermal shock, it cracks and fractures the quartz crystal. So we can't heat it too high. Some gemstones that we learn about, like corundum, can tolerate a lot more heat, and we can heat corundum up to temperatures approaching 2000 degrees Celsius. But with quartz, we can't really go much higher than about 600 degrees Celsius. But with quartz, once it becomes yellow, if we continue to heat it a little bit more, then it will become colorless. And then if we continue to heat it a little bit more, it becomes what we call schillerized. Now, without, damn it, I've got it on this Screen. Can anyone guess what I mean by the term schillerized? What does the word schiller remind us of? Moonstone, the sheen that we see in moonstone. So it becomes schillerized. It starts to develop a little bit of a blue glow on the gemstone with a colorless background. And it's sold as an imitant of moonstone. And this is an example here of schillerized quartz. I don't think it's the most impressive imitation of moonstone, but it certainly gets around. And I remember my first trip to Sri Lanka, just after I did gemology here, walking around all the tourist spots. There were sellers wanting to sell, moonstone pendants, and they had a big lighter, and they went, look, it's real stone. It doesn't melt. It's real stone. No, it was schillerized quartz. And I wish I had bought a bucket load of it back then, 20 years ago in Sri Lanka. But I knew my gemology, and I knew it wasn't real moonstone, and I didn't want the schillerized quartz. Now I want the schillerized quartz. Citrine. Citrine is the yellow variety of quartz. Majority of citrine on the market has been heat treated from amethyst. Naturally occurring citrine is considered very, very rare. People who belong to lapidary clubs, people who fossick for gemstones, if they find citrine crystals, they're not going to have been heated, but the commercial production that all gets processed in Thailand and in large volumes, that stuff has all been heated. Apparently, one of the ways to tell these two apart, or one of the only ways, is that the heat-treated citrine does not exhibit any dichroism, whereas the unheated citrine apparently has strong dichroism. Now, I haven't seen enough naturally occurring citrine to verify if that is actually true. That is one of my lifelong missions, to find enough naturally occurring, strongly dichroic citrine to be able to show you guys, but unfortunately no. One of the things that, if it is present, will verify that it has absolutely been heated is the presence of zebra stripes. So zebra stripes is a feature that we see in amethyst. It's due to the separation of the Brazil law twin planes, which causes a tiny little internal fracture that is then healed. So it's very fine, tiny little liquid-filled capillaries in a zigzaggy pattern that occurs in amethyst. But if it was in the amethyst before it was heat treated to turn it into citrine, then that same feature will be present in the citrine. So if we have a zebra stripe inclusion in a citrine, we know for sure that that's been through a treatment process, because zebra stripe inclusions are not seen in naturally occurring citrine.
Could it have been a naturally occurring heat process though?
Potentially.
Sorry.
Potentially, I know. What we say about heat treatment is that it's finishing off the job of nature, that we're not actually doing anything to the stone that may not have happened naturally to the stone. But quartz gets a little bit more complicated than that, and I got to admit I don't understand all of the mechanisms. But the amethyst in particular has Brazil law twinning, and the citrine does not. And I don't know why naturally occurring citrine does not contain Brazil law twinning, but there is some really high-level scientific reason as to why that is. When we come to talk about ametrine, which is the citrine and the amethyst together, when we have that in a sample, we get triangular segments alternating under the major and minor rhombohedra. So triangular segment of amethyst, triangular segment of citrine, amethyst, citrine, amethyst, citrine. The amethyst sectors always have Brazil law twinning. The citrine sectors never have Brazil law twinning. It's one of the ways that we can tell natural ametrine from synthetic ametrine, because the synthetic ametrine, both amethyst and citrine sectors are untwinned. So I don't understand why it is that citrine doesn't develop the Brazil law twinning. But heating the material won't remove the Brazil law twinning. So no dichroism in treated citrine, and that's fairly common for any material that has been treated. We often find that the pleochroism has been altered and sometimes reduced from what you expect to see. So if you expect to see a dichroic response, you might see a monochroic response, or if you expect to see a trichroic response for that particular mineral, the heat treatment may result in a specimen that is dichroic, not trichroic. So it often reduces the amount of pleochroism. Ametrine. Ametrine was discovered in 1980 in Uruguay. It is now from Bolivia, from the Anaheim mine. I think if I got that correct. Initially, the material was assumed to have been synthetic or somehow artificially created. And there's still a lot of talk on things like Reddit or other pages, chat kind of groups, where people assume that ametrine is heat treated to get that effect, that somehow they heat half of the stone, but not the other half of the stone.
The sample that we were passing around that had yellow and purple in it. Yeah.
So
That was this one?
you're passing that one around?
No, that's me. Passing that one around.
Okay, cool. So there has been peer-reviewed articles written on the Anaheim material to prove that it is naturally occurring and not treated. There has not been any peer-reviewed scientific article that has proved the existence or the process of any treatment that can create an ametrine out of natural material. But I'm willing to say that the question's still out there. We just haven't been able to prove it, and no one's come forward to show in their lab how they may be treating the material. And quite often with treatments of gemstones, the treaters who are treating the gemstones, they keep it a closely guarded secret what they're doing. They don't want to tell people what they're doing because they're often taking material that's not worth as much, changing the nature of the material, either the color or the clarity, and then potentially selling it for a lot more. So they don't always want to tell people what they're doing. But for the ametrine, there's no peer-reviewed article that details the treatment process. This is a photo that I got from the internet because I really, really love a piece of ametrine that looks like that, but unfortunately I don't have one as perfect as this. So this is a piece of ametrine that is sliced perpendicular to the optic axis. So when we're looking down the center of this stone, we're looking down the direction of the crystal, down the C crystallographic axis, which is also the optic axis of the material, and that's really, really important. Spot question. What happens if we put a gemstone on the polariscope and we are looking down the optic axis of the material? Interference colors, yeah. So we put this type of material, a slice, on the polariscope, we see interference colors. Now, I just said a few minutes ago that with the natural material, the amethyst is twinned according to Brazil law, and the citrine has no twinning or does not have Brazil law twinning. It may have Dauphiné twinning, but no Brazil law twinning. What is the pattern that we see under crossed polars when we have Brazil law twinning in amethyst?
Stripy rainbow.
Airy spiral.
The airy spiral, yes, we get the airy spiral with the conoscope, but before we look at the conoscope, the interference colors that we see in the gemstone have a pattern.
Stripy rainbow.
Stripy rainbow, yes. Okay, stripy rainbow, yes. It's also called Brewster angles. So it's like triangular witches' hats that are superimposed on each other. We'll see this kind of chevroning triangular thing. You might be able to pick it up. I'm just going to turn these lights off. We sometimes get the color bands in the amethyst also follow that direction. So can you guys see here? This chevroning, alternating, triangular growth pattern. So that's following the Brazil law twinning. And when you put this under the polariscope, this lights up with that triangular pattern in the Brazil law twinning. And the citrine does not show any of that Brewster angle in there. When this material is cut, quite frequently it is cut as a rectangular emerald cut with a 50-50 split. So taking a large piece of material like this, they'll be cutting from this segment. It's not very frequently cut so that you get multiple quarters, because if you get multiple quarters, it tends to blend the colors a little bit more, and people like to see that 50-50 split. This is a piece that's in my collection. We do have quite a lot of natural ametrine next door that you guys will play with, particularly with the polariscope. We've got some in the polariscope set. So this is a natural piece of ametrine cut in a rectangular step cut with a 50-50 split. When we put it under crossed polars and find the optic axis, the citrine component just shows the interference colors with no associated pattern. And the amethyst sector has this Brazil law twinning Brewster angles. Can you see this has got a slight triangular nature to it? So this pattern here confirms Brazil law twinning. And the fact that we have Brazil law twinning in the amethyst and not the citrine confirms that this item is natural. We then can take out our conoscope, and because the citrine does not have any Brazil law twinning, we get a bullseye. And because the amethyst does have Brazil law twinning, we get the airy spiral. Whoops.
Sorry.
If it was a synthetic ametrine, there would be no Brazil law twinning in either segment. So we would have no Brewster angle, and we will get bullseye in the citrine and bullseye in the amethyst. And this is some more pictures of ametrine. Michael Diber is one of the faceters that has had a really, really great career in innovative faceting and carving and fantasy cuts. And this is one of his examples here of using ametrine. And this is a piece of rough that obviously hasn't been a full crystal, so it hasn't been sliced. Okay, prasiolite. Prasiolite is a fancy word that we give for green colored quartz. On the market, it is sometimes referred to as greened amethyst, which is a misnomer that we really don't like in the gemology business. Sometimes it can be referred to as green quartz, which is better than greened amethyst, particularly greened ED. Greened amethyst means that it has been heated or treated from amethyst to derive a green color. The green color originates from a heat treatment process. The heat treatment of this material originates from amethyst that contains ferrous iron, which only comes from a few locations. The vast majority of amethysts have got ferric iron as the coloring agent. And if you heat amethyst with ferric iron, Fe3+, then it'll derive a yellow color, whereas you heat amethyst with ferrous iron, Fe2+, it's more likely to attain a green color. There's quite a lot of this material on the market, and not all of it is the result of heat treatment. A lot of it now is also a result of irradiation. And we have got no tests to show or to prove whether it's been irradiated or whether it's been heated. But the green color is not or does not occur naturally in any quantity or any particularly large sizes. You can get small stones, but very rare and few and far between. It's like natural citrine, very, very, very rare. But the vast majority these days, I believe, is irradiated. Smoky quartz. Smoky quartz is a variety of quartz that is brown in color. Whether it's a light brown or a dark brown, they are all smoky quartz. Smoky quartz can also be heated to try to change the color. If it's heated at 200 degrees, it will turn into citrine, and if it's heated to 300 degrees, it may become colourless. So this is the part of the presentation where we actively encourage students to perform experiments. 200 degrees is well within the temperature range of an oven at home, whereas 400 to 500 degrees is a little bit beyond the home oven capability. So if you have a piece of smoky quartz and if you want to see if it'll turn into citrine, you can heat it in your oven for 1 hour at 200 degrees. But there's a few technicalities. I mentioned earlier that quartz is susceptible to fracturing, to thermal shock. So if it heats up too fast, it will crack. If you put it into a hot oven on a metal tray, the metal will heat up very, very fast, a lot faster than the stone, and will cause the stone to crack. So what you want is a nice gentle increase in heat, and then you want a nice slow, gentle decrease in heat. So the best way to achieve this is next time you are roasting a chicken, to put your quartz in with the stuffing in the chicken, and hopefully it'll come out citrine. That always gets a laugh. I don't understand why. I personally have not tried that experiment. We have had a few students in the past who have. Adele has sometimes provided the material to treat. If anyone is game, just don't eat the stuffing that's surrounding the quartz. We're not quite sure about that, but the chicken's safe to eat.
If you just put the stone in when the oven's off and just let the oven heat up with
The metal plate.
So the middle heats up
The-
more than the crystal side.
The metal will heat up very, very fast, and it'll crack the stone. So the chicken and the stuffing provides that little buffer.
Gradually increase the temperature of
You
the oven.
could gradually increase the temperature on the oven.
I might try this at work with the kiln with a tub of kitty litter.
There you go. That would be really, really good.
Because that's what you do to get strain-free glass, is you put it in a thing of hot kitty litter.
Yep, and if you've got the kiln, then you might even be able to try the amethyst and get it to go to citrine as well. Sorry?
What's kitty litter turn into?
Oh, the kitty litter is the kitty litter is just a little bit of a buffer. It protects the stone from thermal shock.
Actually, clay. That will do it.
Another word that we're going to throw at you, and in end of year exams, they sometimes like to get a little bit fancy and ask words, stones, varieties that are not that common on the market at the moment.
Right.
Cairngorm. Does anyone recognize this word? I'm hopefully kind of looking towards Mitch. Nope.
Well, it says it's from Scotland. So.
It says it's from Scotland.
Isn't a can a burial mound?
Yes. Yes. But the Cairngorm material frequently found in antique Victorian jewellery, the silver Scottish jewellery. Queen Victoria was a fan of Scotland and wore Scottish jewellery, Scottish agate jewellery. And Scottish agate jewellery, this is an example here of pieces of agate, also set with the quartz from the local area that was a kind of reddish brown colour and went by the name Cairngorm from the region in Scotland. So it's colour of quartz that is usually seen in Scottish jewellery, antique Scottish jewellery.
How does it compare in colour to like Madeira citrine?
I want to say slightly darker redder, but probably very similar.
And what is Madeira citrine?
A darkish orangey, lending towards smoky.
But like, is it chemical composition much different to normal citrine?
No, it's still colour centres associated with iron.
So is Cairngorm the same thing as carnelian?
No, No, carnelian is a form of cryptocrystalline quartz. It's an agate without the banded effect. Whereas the Cairngorm is a single crystal. So your carnelian is an aggregate of fibers, thousands and thousands and thousands of tiny little microscopic fibers, and the Cairngorm is a single crystal. Another word you might not...
There's another one. Another
Yes.
one I see a lot is lemon quartz.
Yes.
That's got like iron in it.
Yes, that's also iron. The lemon quartz is slightly different to the citrine. It's a slightly lighter color. My waters tell me, because it's all kind of with the green quartz and the lemon quartz, I think it's all irradiated to get that light yellow color and that consistency. This material is often very, very consistent in color, and natural quartz tends to be very patchy and banded in color. So when you see that consistency, my little spider senses tell me treated, irradiation, or synthetic. Was there a question at home? No. Question at home? No. Okay, so Morian is the black variety of quartz. It's not actually opaque black. It's just very, 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 very dark smoky. So you should be able to get color when you shine a strong light through it. Rose quartz, slightly cloudy, slightly pink variety of quartz. Really exciting. It can show very strong asterism. It can show both diasterism and epiasterism. So it can show in transmitted light and in reflected light. Now we're going to, next week, we're going to go on to quartz treatments.
Familiar with the way that they can use amethyst deposits to find locations of uranium underground?
No, I haven't read any information about that. I wouldn't be surprised because of the natural irradiation with the amethyst.
Yeah, they just look at the direction of the black faces on the amethyst, and then they follow that under the ground.
Oh, cool. That's awesome.
Yeah, I learned about that from the geologists in Broken Hill working on that.
Yeah, that doesn't surprise me. There's lots of really, really cool information and stuff in Broken Hill. It's a really interesting area for minerals and for deposits and a whole range of stuff. Really exciting. Okay, we need to kind of push on. We're going to jump straight into treatments. We've talked a little bit about how amethyst is heated to achieve citrine, and then you irradiate citrine to go back to amethyst. I've got a couple of recipes here because they're a little bit fun. The treatment processes that we use on gemstones, some of the most basic treatment processes that we use still to this day, more or less, slight variations on the original recipes, but they're almost the same type of process. So treatments to stones is something that has actually been done for hundreds, if not thousands of years. And the very first treatments were done to try to change the color of gemstone materials, not to improve the clarity. Nowadays, a lot of our more advanced treatments will focus on improving the clarity to make a cleaner looking stone. 2,000 years ago, they were more concerned with the color of the gemstone material. So to change the color of a gemstone material, some gemstones materials will respond to just heat, but some gemstone materials will take on dyes, and some gemstone materials you need to induce fractures in them in order to dye the material. So a lot of the treatment processes to quartz, the cryptocrystalline quartz, the agates, they're actually porous and they will readily take on dyes. But the crystalline varieties, the rock crystal, we talked a little bit about thermal shock. If we heat it up to too high a temperature and then cool it down too quickly, it induces fractures in the material. And those fractures can then be dyed with a colored material to try to change the color of the look of the piece. That process of crackle quenched dyeing has been around for about 2,000 years. And we've got recipes and documentations that go back to 200 BC that list treatments for stones. So here are some of the historic treatments. We put the stone into a bowl, put it on another bowl as a lid and seal the joint with clay. Let the stones be roasted under supervision for a little while. Then by degrees, remove the lid and pour vinegar and alum on the stones. After this, colour the stones with whichever dye you desire. So we're roasting the stones, we're heating them up, and then pouring vinegar and alum on the stones. When we pour a cold liquid onto a hot stone, it induces the fractures, it quenches the stone, and then we can dye the stone. The dye will penetrate those fractures.
What's color?
Aluminium oxide. Another recipe, let the stone stand for 30 days in putrid urine. Remove the stones and insert them into soft figs and dates. These should now be treated on the coals. Blow therefore with the bellows till the figs or the dates burn and become charred. So if the dates are burnt and charred, the stone inside is getting pretty hot. Then seize the stone, but not with the hand. So if you seize it with the hand, you're going to burn your hand. So you have to use the tongs. And while it's still warm, place it directly into the dye and let it cool there. And the dye should be a thick paste. So again, it's introducing thermal shock. The stone is cracking because it's cooled down very, very quickly. And the cracks reach the surface of the stone, which is really, really important. Surface-reaching fractures mean that the dye can then enter into those surface-reaching fractures. So these recipes sound a little bit ludicrous because we don't use stale urine or putrid urine. They didn't quite understand the scientific processes to be able to explain thermal quenching, but the process that they were doing was quenching the stone and dyeing it.
Well, the urine was used in ancient Rome for their laundry. It was actually distilled for the ammonia and bleaching all the clothes.
There you go. So they had plenty of it.
And toothpaste.
Yes, Kavitha?
And toothpaste.
And toothpaste.
They use urine.
Urine for toothpaste. Oh. Well, I know they used to use it during the war as an antiseptic on wounds as well.
Jellyfish sting. Blue box sting. You piss on it.
Blue box, yes. Yeah, the jellyfish, the blue box jellyfish. Yeah. There's another recipe that says to soften the crystal, take goat's blood and dip into the crystal which you have first heated over a gentle fire until it is to your liking. So whether that's medium rare or well done, I don't know. To soften or loosen means to crack the stone so that the dye can enter the crack. So we're quenching the stone. And the dyes that we used were copper or other metal salts. These days, some of the dyes that are used on materials can be synthetic dyes or they can be organic dyes. And depending upon the material that's being dyed, sometimes the organic dyes may fade, be UV non-stable to UV and may fade fairly quickly, but that's something that we can talk about a different day. The early treatments were not meant to improve the stone being treated. They were actually causing fractures in the stone. They're not healing anything in the stone. They're not improving the clarity, but it's a mechanism to try to change the color of the gemstone. So they're wanting to make it look like another stone superficially. And there were no gemologists 2,000 years ago, so no one was looking for color concentrations along fractures, which is the telltale sign that we look for today with a quenched, crackled and dyed quartz or any material that has been dyed, is that we look for color concentrations along existing fractures in the stone. There's a quote from Pliny that I absolutely love because this was written almost 2,000 years ago. And Pliny says, in a word, to transform one stone into another To tell the truth, there is no fraud or deceit in the world which yields greater gain and profit than that of counterfeiting gems. So now we have things like glass fracture-filled rubies, we have glass-filled diamonds, we have coated topaz, we have coated moissanite of all things, and coated cubic zirconia. There's a whole lot of things that we can do to gemstones to try to deceive. But did I show you my favourite stone, my new favourite stone? I got it like 3 or 4 weeks ago, so I may have shown you a really gorgeous piece of watermelon tourmaline slice.
Yeah.
So a doublet made of natural quartz that's been hand painted and glued together. Again, another counterfeit gemstone example. I'm not sure how much profit they made because I bought them a pair for $20 US with free postage, but they must have been making enough money to cover the wages. Anyway, so with all the treatments on stones, results will vary between samples. This can be due to impurity or structural defects with individual stones. So not just quartz, but any stone that we treat, results will vary. And they'll vary depending upon the individual stone and individual chemical properties of that stone, what trace elements are present and how it's going to react. So the big one that we need to learn about with quartz is the heat crackled quartz or the quench crackled quartz with dyeing. So stones are heated to a high temperature. They're then dropped in an ice bath to cool them down really quickly. That quenches the stone. It induces thermal shock and the stone cracks. Those cracks can then be dyed. That dye can either be in the liquid that it's dropped into, or it can be dyed later as a secondary process. So dyes are introduced by using coloured solution in place of the water, but there can be different processes. The dyes that are used are usually very unnatural looking. So they're like a bright blue colour, a bright red colour, a bright green colour. For quartz, they're colours that you don't normally see. And then because quartz itself is not porous, the dye doesn't penetrate into the crystal lattice itself. It only coats the surfaces of those fractures within the material. So we look for colour concentrations along existing fractures. What have I got here? Process for producing crackled quartz is given a detailed account in 1672, and it's a process that was described as early as 400 AD, and that process, although there may be some modification, is still used today, and you can still get quenched quartz fairly routinely and fairly easily today, particularly if you go onto eBay. And particularly if you want a really nice looking emerald, particularly if you use the words certified natural emerald. So use the word certified natural emerald and look for something that's less than $30 US. You'll come up with really nice big pieces that go up to about 5 carats, 6 carats. You'll find all in the photo concentrations of colour in the fractures, and it'll come with a very nice certificate saying that it's untreated emerald. And when you get it, it's got a very nice bullseye on the polariscope. Crackled quartz. We have actually had students a few years ago prior to their course buy this material, and then like first, second week of Gem 1 ask us to verify that it's emerald for them. And we're like, well, that's why you're learning gemology, because it's not emerald. Anyway, heat and irradiation. You'll get a chance to see some of those examples because they are in the lab. Heat and irradiation, they're opposites of each other. They're two sides of a coin. Whatever we create with irradiation can be destroyed with heat, and vice versa. If we create a colour with heat, we can destroy it with irradiation. And it works because of colour centres within the material, or the opportunity to create colour centres within the material. So to create a colour centre, there has to be an interstitial ion to trap that electron once the electron has been ejected from another ion that does not usually produce color. So we're looking at elements that are not transition elements. Now, some color centers are weak and unstable. So that means the amount of energy required to reverse the color center is not a large amount of energy. So what does that mean? That means that the energy from the sun, the ultraviolet rays in the sun, may be enough to reverse the effects of the treatment process and cause the gemstone to lose the color that it acquired through treatment. That process is termed bleaching or fading. So gemstones may fade. Quartzes have a relatively strong color center. They do actually fade. Amethyst will fade if it's left in a shop window under very intense light or under direct sunlight for a prolonged period of time of maybe up to a year to a couple of years. You'll find that your amethyst will fade. But in general, for everyday wear, it's considered safe as long as you're not spending 24 hours a day in absolute full sunlight. So quartz is considered relatively stable. Some other gemstones that have fading color centers, the kunzites that are treated by radiation, often fade very quickly. There are some naturally occurring topaz. The brown topaz have an unstable color center and will fade back to colorless. There can be some natural yellow sapphires that have unstable color centers that can fade. We can get some blue beryl that's termed Mashishi beryl, which is actually spelled with an X in there, Mashishi, M-A-X-I-X-E. That's a naturally occurring blue beryl with an unstable color center that fades to colorless. And it's usually a very strong blue color, but it fades very, very quickly. But on the market at the moment, in really strong blue-coloured aquamarine, which often gets termed Santa Maria aquamarine, the really strong blue colour, Swiss blue topaz colour, is often irradiated and it's an unstable colour centre and will fade fairly quickly. So there are lots of gemstones that can have unstable colour centres, and there's lots of colours that may not retain their original colour after they've been bought.
Is there a way you can tell if Santa Maria was being
Yes.
on the spot?
No. It needs to be tested with advanced instrumentation. One of the tests that can be done is with UV-Vis NIR, which is an advanced digital form of the spectroscope that we have. And we look for particular peaks that are consistent with the treatment process. That instrument costs about $25,000, and Victoria has just purchased one about 2 weeks ago, which will be delivered hopefully in about 3 to 4 weeks.
Yeah.
Then I'll get to play with it. But from the reports that I read, because we just had a situation a couple of weeks ago where we were asked an opinion at my workplace, and we did a little bit of research. I thought it was FTIR, but when I found the article from GIA and it was UV-Vis, do you know how excited I was? That in like 3 weeks' time, I'll actually be able to test these stones, potentially for a service for the trade, and say that this stone conclusively has been irradiated. At the moment, Bill at Gem Studies Laboratory in Sydney can perform that service as well, but you'll have to send the stone up to Bill if you're wanting to know. But there have been instances over the last couple of years where jewellers in Melbourne have wanted to know and have sent it to Bill, and he's been able to verify. So unstable.
Before I buy it.
Generally, if the price is too cheap,
Yeah.
that's what we found in the last couple of years. We had a jeweler who, there was a traveling salesman from Pakistan who was offering him very dark colored aquamarine that was far too cheap, and he bought a piece just to try it out, and we sent it up to Bill, and it came back, irradiated material and unstable color center. But it was a quarter of the price of material on the local market. It was ridiculously cheap, and of a color that's unattainable in the local market as well. So if the color's too good to be true and the price is ridiculously cheap, something's going on.
Yeah.
But I am excited about being able to test that as well. So color centers, just to revise. I got that mixed up, didn't I? Color centers involve, just to revise, one electron missing from a normally occupied position on an atom that usually doesn't cause color. So where we have a pair of electrons, and that's called the whole color center. Before the electron is ejected, it's actually called a whole color center precursor, because every atom that has a pair of electrons has the potential to have one of those electrons removed with irradiation, because the radiation is a really high intensity energy source. And then once that hole is created, if there is a trap precursor, then that electron can be trapped elsewhere. And then it just depends on how strong the strength of that trap. If that trap is really, really strong and it takes a lot of energy to reverse that process and eject that electron and send it back home, then that's considered stable. But if it's a weak color center, then the amount of energy required to release the electron is very, very minimal.
Sorry, what determines the strength of the?
Just the chemistry of the atom and which elements are involved in the color center. It's a little bit complicated,
Lots of time to say.
yeah. So it's
Is that like how many electrons are in its valence shell? Or?
not how many electron volts of energy are required to eject the electron from orbit.
Right.
Okay. A little bit complicated. But for now, for gemology, we're just going to kind of learn that irradiated kunzite is usually unstable. Irradiated quartz is usually very stable. So it's just learning which materials may fade and which ones won't, and just being aware of materials on the market. So a whole color center precursor is any atom that contains a pair of electrons in the valence shell, and an electron color center precursor is any interstitial element or any element that can trap that electron, that can take that on board. And the role of irradiation is merely to transfer the electron from one location to another location, from one electron shell around one atom to another electron shell around another atom. And that results in the light interacting differently with the material and the light being absorbed differently, which results in color being seen. So I'm going to skip over this. Fading and bleaching occurs when the heat or energy excites that electron enough for it to leave orbit, and then it might wander back home to where it originally came from. And that's going to reverse the process, and you'll lose any color that's being developed. And I've said all of that, so I'm going to continue. Smoky quartz, the color of smoky quartz from the image that we saw earlier, that I said this is actually smoky quartz because I can see that it's an aluminium atom, not an iron atom, or an iron of iron.
Iron with an iron.
Iron with an iron. Anyway, so the smoky quartz, the color is caused by a color center associated by aluminium. The amethyst and the citrine is a color center associated with iron. And the rose quartz, of all things, is a color center associated with titanium, which causes the pink color. Anyway, I'm going to skip over this a little bit because we've done this to death now. So amethyst is the iron. Green amethyst has just got the different valency. We're looking at Fe2 plus rather than Fe3 plus, and rose quartz is colored by titanium. So color center involving titanium. So that's actually one school of thought with rose quartz. I want to mention very quickly, you won't read in your notes, but there are rose quartz. Another school of thought on rose quartz is that the pink color is derived from the presence of dumortierite inclusions within the stone. Very, very, very microscopically fine fibers of dumortierite. A dumortierite is usually a blue-colored mineral, but it's assumed that may contribute to the pink color of the rose quartz. And there may in fact be two different varieties of rose quartz, one colored by dumortierite and one colored by color centers associated with titanium. And with all of this, it may take more research to look into that a little bit deeper, but as quartz doesn't have enough funding behind it, not as much funding as things like ruby and diamond, then these things take a little bit longer for research to be done. Okay, another treatment that we're going to discuss about quartz is coatings on the surface. There's sputter coatings and coatings of metal ions. Has anyone heard of aqua aura? Yep, nope, yep, nope. A few yeses and a few noes. Okay, aqua aura was a treatment process that's been around for a couple of decades that has been done on quartz crystals. The initial treatment process was on quartz crystals, and aqua aura is a process via which they coat the surface of the quartz crystal with a very, 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 very thin layer of gold atoms, only a couple of atoms thick. And the presence of the gold atoms on the surface of the quartz crystal creates a constructive and destructive interference pattern and results in an iridescence seen on the surface of the quartz crystal. So this here is an example of aqua aura, and we can see that we've got a very metallic luster on the surface, which is coming from the gold. And we've got these iridescent colors of blues and greens and purples. Let's have a little bit of the oil on water effect. Because this treatment, the application of these atoms is so thin and so fine on the surface of the material, they are easily worn off. So any surface damage, any abrasion, loses the gold from the surface, and that results in the loss of the color. For these crystals, they usually sit in a cabinet, so you don't usually have, if you sit there and just look at them and don't handle them, they're not going to get damaged. But when they're in a piece of gemstone being worn in jewelry, there's the opportunity, more opportunity for damage. So after the aqua aura was done on quartz crystals, they then started applying the same treatment to gemstones. And my belief is that the first gemstone to be treated was not quartz, but was in fact topaz. Has anyone heard of the mystic topaz? Mm-hmm. So mystic topaz is the same process, but it's not done with gold, it's done with other metals. But it's a thin application of metal ions on the surface of the gemstone, which creates an iridescence from constructive and destructive interference. Once they did the mystic topaz, they then played with the recipe a little bit, and they tried different combinations of different metals and worked out that they could make a whole range of different colors, either a solid single color or different iridescent colors depending upon what metals they used in the application. From the mystic topaz, we then got a whole range of colors in topaz, and then they started doing the same process to quartz as well. And as well as quartz, they also do it to, so you've got topaz, you've got quartz, they do it to tanzanite, they do it to moissanite, they do it to cubic zirconia, and they do it to diamond. There's been reports of pink diamonds on the market that have been surface coated, We have an example downstairs in our diamond collection of a coated pink diamond. They haven't been around for a while, but when they first hit the market, a couple of people bought them unintentionally, thinking that they were natural coloured pink diamonds. What we look for, regardless of the stone that's been treated, the hand lens features are all consistent, and it's a very, very easy treatment process to identify. We look for a metallic luster on the surface of the gemstone. So a luster that's much, much higher than what we would expect from the gemstone material. We look for signs of surface damage. Anywhere that's got any scratches or abrasions leads to loss of color of the, from the gemstone material. So that's very easy to recognize with a hand lens. The other thing, I don't know if you can quite make out here, it's got a speckled type of color. We've got a blue face with little kind of greenish white dots on the face. Can you see that? So that's a result of the sputter coating. You get this kind of speckled appearance on the surface. So metallic luster, speckled appearance, and loss of color where you get surface damage are your identifying features, and those features are the same regardless of what gemstone material it is. Now, another thing that I'm going to mention that isn't in this PowerPoint, but I'm going to get you guys again next year in Gem 2, and we're going to talk about treatments. With gemstone materials, we've got stones that are faceted and cut for total internal reflection of light. The colour that we see comes from the pavilion of the stone, not from the crown of the stone. So when we look at a GTD, the colour that we see is from the pavilion of the GTD. We don't see the red almandine garnet in the crown. So the first generation of these gemstones, they coated the whole stone, and it was very, very easy to recognize in jewelry because the crown was also sputter coated. But then they started to learn after a couple of years that they were wasting a lot of precious materials of these metals in treating the crown of the stone when they only needed to treat the pavilion because the color was coming from the pavilion only. So if you've got gemstones that are set in jewelry, you're unlikely to see this effect on the crown of the stone. You'll see it on the pavilion. If it's set in jewelry, unless it's been damaged during the setting process or from parcel wear before it was set, the setting protects the stone from other damage. So it may be longer to see the effects of any damage to the stone. But if it's loose parcel wear with rubbing against other stones, you'll lose that surface coating very quickly. So, yeah. Now, this is just a summary of different treatments that can be done to gemstones. Composites. We don't need to talk about composites. You guys know all about composites. I should put in here the picture of that quartz composite of the tourmalines. They're cute. Surface coatings, foil backs. Foil backs is where they put a highly reflective silver metal on the pavilion of the material. It reflects a lot more light, so it makes it look a lot more brilliant. But this is just a summary of all the treatments that we've discussed tonight. This is a little summary showing the temperatures. So to go from a smoky to a greenish yellow, you heat it from between 140 to 280, or to go to a bluish greenish color. I'm not sure about the blue. 160 to 280 also. It depends on the coloring agent in the smoky and how much iron is present. Interestingly, if you start out at colorless and you irradiate colorless, you usually derive a smoky color. That's because smoky quartz is a color center associated with aluminium. So you've got silicon, oxygen, and a small amount of aluminium. None of those elements are transition elements, and colorless quartz may contain enough aluminium as a whole precursor or a trapped precursor, so that when it's irradiated, it actually acquires a smoky color because of the aluminium in the quartz. And with the amethyst, we heat it to go to citrine or you radiate it to go back to amethyst. So that's just a little handy chart for you to remember those treatment processes. Now we're going to talk about synthetic quartz. Where are we at? I'm only 8:45. This is good. We can do this. Synthetic quartz. I love synthetics. I love synthetic quartz. I just think they're really, really cool. It's not part of the Gem 1 syllabus, but I think you guys can handle a little bit of information about synthetics. You won't be revisiting quartz in Gem 2, which is why I kind of slip in the information about synthetics into Gem 1, just so that you've kind of got it there in the back of your head. The way that we manufacture quartz is via a process called hydrothermal growth, and that process is the same as what is used to grow beryl crystals and is sometimes used to grow corundum crystals as well. So the hydrothermal growth process, the apparatus that is used, is consistent, but I need you guys to also realize and understand that there's a hell of a lot of synthetic quartz on the market out there. And we're going to talk about the limits of what we can do with gemology in actually identifying these synthetic properties, synthetic origins, gemstones. Start off with a P word there, and then I didn't know what I was going to say. Quartz is the second most widely used electronic material after silicon. So I mentioned earlier quartz watches. It's got a little quartz crystal in there that is oscillating, that keeps the time and counts the seconds. It's because of the piezoelectric effect in quartz that when placed under mechanical stress derives an electrical current. Was that a question at home?
No, it was a little dissection of that, because piezoelectric characteristic is basically stress or frequency or vibration.
Yes.
And it turns it into electric pulses. This is
So it's under mechanical stress, and then it vibrates and oscillates, which has a frequency, and that frequency can be used by electrical devices.
Yeah, that is in your watches and your devices, in your materialistic stuff.
Yes.
But basically, this is where the principle of your birthstone comes from, because when you wear these, your frequency and vibration affects, which is why you wear these birthstones. So it connects you from the magnetic grid of the earth to the cosmic grid. This is where my question went a bit apeshit before and became ambiguous. But the question is, this is the principle in your transducers, that in frequency and vibrational healing, this is the quartz. This is what my puppy's tumor was cured with, this principle that I used, and the vets were quite surprised. And this is what's in your med beds or your med pod technique from the 80s that's come to your med beds, that's coming into your hospitals now. So basically it's the frequency and vibration that goes through your quartz and produces these little electrical impulses that heal you or connect you. So that's mentioned the two controversial birthstones. They are both producing these frequency and vibration in opposite directions.
So it is really fascinating, the vibrations through quartz crystals.
Yes.
But that's going outside of what we study in gemology.
Yes.
Yeah.
But it is these rocks that's actually producing these vibrations to trigger this piezoelectricity in your devices and your body and your everywhere else, wherever your piezoelectricity is. So my question is, do we get to measure this stress?
No, we don't measure that in gemology. We don't have any instrumentation in gemology to measure those vibrations. But they are used in all kinds of electrical devices.
Yes.
Quartz is even used in your mobile phones to use the Wi-Fi networks and other kind of elements of mobile phones. So it's used in radios, it's used in watches, it's used in mobile phones, it's used in sonar, it's used in so many devices. And because it is so integral to a number of electronic devices and computers included, the quartz that is used is manufactured. So it's grown in, we don't really like to say labs, but lab grown. It's not grown by scientists, stirring pots on a stove. They actually use very large, what they call autoclaves, and can grow quartz bricks that are quite large, and they can grow like 60 quartz bricks at a time in these massive underground autoclaves. Back in 2000, and it's sometimes difficult to get updates on these figures, but back in 2000, it was estimated that 3,000 tons of quartz was grown that year. And because of the demand of quartz in electrical devices, that quantity only increases every year of the amount of quartz that is manufactured. So it is the most manufactured mineral. Most of it is done for technology reasons, and a small amount of it makes its way onto the jewellery market as being cut and polished in gemstones. But its primary reason for being grown is not for the jewellery industry.
My last question is, what is the stress put on these quartz in the devices, mechanical devices that produce this?
That I don't know, Kavita.
Okay.
It's not my area of expertise.
Okay, no worries.
No problem.
Thank you.
So the process that we use to grow it is called the hydrothermal growth process. The quartz was most valuable during the First World War, and it became one of the most critical areas of scientific exploration to try to manufacture quartz crystals for the sonar and for the radios. They needed to have quartz crystals that were very, very clean and very, very pure. But as well as that, quartz often has twinning in it. So we get Dauphiné twinning and Brazil law twinning. They need to have rock crystal, and it needs to be free of dislocations. So that means irregularities in the crystal structure, and it needs to be free of any twinning, which is very, very difficult to find naturally, the material that was of use for the war effort for these new instruments that were coming online. So they developed a way of manufacturing quartz crystals. And mass production of radio units was then required for World War II. So it was like one of these breakthrough technologies. Today, synthetic quartz is used in almost all electrical devices, including the mobile phones that we carry. It's used to regulate the frequency of electrical signals. So the quartz crystal is important because it oscillates, and the amount of oscillation, the degree of oscillation, is very, very regular, which is why it can be used for timekeeping. So it's used in clocks and watches, computers, radios. It's used in our mobile phones for Wi-Fi and Bluetooth and other communication devices. And the more of these devices that we produce or consume, the more quartz that we need to run these devices. Now, quartz has a melting point of about 1670 degrees Celsius, which is not that important to us as gemologists, but for the people who are manufacturing quartz, it's vital information. Quartz twins are produced where the crystal has formed at temperatures above 573 degrees Celsius. And they want quartz crystals without twinning, because twinning in the quartz crystal means that it can't be used for these electronic devices. So it's manufactured at cooler temperatures below 573 degrees Celsius to make them free of twinning. Free of twinning also means that they have no Brewster fringes or other patterns when we view it under the polariscope, when we find that optic axis. So that's one of the things that we can do to try to separate natural and synthetic quartz. is that they can create synthetic quartz crystals that are colored any color, and they're always going to be free of twinning. You're always going to get a bullseye on them with the conoscope. Because the stones are synthetic, synthetic means that they have identical chemical composition and identical physical and optical properties to the natural counterpart. So that means the refractive index is going to be the same, the specific gravity is going to be the same, the birefringence is going to be the same. Basically, all of the results of all of the testing that we do in the lab is going to confirm that the gemstone material is quartz. But to try to separate the natural from the synthetic can be a little bit tricky. And in some instances, it's not possible to separate natural from synthetic quartz. Some of the things that we look for will be consistent color. We've got a piece of purple amethyst that Adele handed around. It's very richly saturated purple. Oh, no, that's the crystal. I meant the faceted piece.
Oh, you got this one.
Yeah, because that's the ametrine. Ametrine. So if you get a piece of quartz and it's very richly saturated and a large gemstone and it's very clean, if you immerse it in a liquid and you can't see any color banding or color patches, that's potentially a bad sign that it could be synthetic. If you've got a piece of amethyst that's richly colored with no color banding or patches and is showing a bullseye, that's another nail in the coffin that says this might be a synthetic material. But the only way to actually conclusively identify it is to use a very expensive piece of equipment that costs about 50,000 US called an FTIR. FTIR stands for Fourier Transform Infrared Spectroscopy. And that gives you peaks similar to your spectroscope, but it does something slightly different. You look for the water content and the amount of water content in the synthetic from the natural. But it's not always conclusive to be able to separate the synthetic from the natural. So it is really, really, really tricky. The picture here on the screen is showing a diagram that illustrates the apparatus that is used for quartz production. This is called an autoclave. It's got essentially a canister in the center where the quartz crystals are growing. They're growing in a liquid. We've got two zones within this area. The quartz crystals are growing in the top half of the area, and they're growing on wire with a seed plate through the center. If we hand around again the blue crystal that's in Adele's hand, you can see at one end of the crystal, it's got a tiny little bit of wire. And if you look down the center of the crystal, it's a light blue color, but it has a colorless plane right through the center. So that colorless plane is a seed plate. That seed plate can be made from either synthetic quartz or from natural quartz. But the feedstock that's placed in the base of the autoclave is usually natural material that's of a very high quality and has been cleaned to have any impurities removed. The autoclave is heated, and then there is what's called a temperature gradient created. Temperature gradient means the temperature is not consistent within the autoclave. It's controlled so that it is slightly hotter at the base of the autoclave and slightly cooler at the top. So the temperature will melt and dissolve the nutrients. And then because of thermal convection, the liquid carrying those nutrients rises. And as the liquid rises, it's also cooling because of the temperature gradient that's controlled by the instrumentation. So as the liquid cools, it becomes what's called supersaturated. And then the quartz materials that are dissolved in the liquid start precipitating and growing on the seed plates that are in the upper part of the autoclave. And so that process continues and continues until the quartz crystals grow large enough, and then the autoclave is opened and the crystals are removed. Seiko is one of the organizations that grow quartz crystals in Japan. And if you get onto YouTube and search for Seiko and synthetic quartz manufacture, there's a really cool little video where they visit the Seiko factory, and they're present when one of these autoclaves are unlocked. And then a big mechanism kind of just draws up all of these quartz crystals, and it keeps being lifted into the roof. And these quartz crystals are the size of bricks. They are enormous quartz crystals, and there's just row after row after row of these quartz crystals. So growth is conducted in a steel pressure vessel called the autoclave. Supply of nutrient material is usually uniform in size and must be very, very clean. So it's usually treated to remove any impurities within the material. So it's cleaned with a chemical rinse. The seed crystal, which is always present, seed crystal is just a thin rectangular strip of material. It will be natural or synthetic, it doesn't matter. And the seed crystals hang in the upper half of the autoclave. The crystals usually have the seed removed before the crystals are used and sold, and that seed can then be reused in other materials. Sometimes it's a little bit amusing for gemstones that are sold within the industry. Oh, you might hand around the slice of ametrine and the faceted bicolor citrine in the tub. Oh, and the tumbled. No, the slice. Yeah, that one. And the tumbled that we bought up in Queensland. They sold it as tumbled natural quartz. It's hilarious because it's rectangular.
Did you say this is a synthetic quartz crystal?
That's a
synthetic.
Yeah, that's a synthetic quartz crystal. You'll also notice on the surface of the quartz crystal, it has little kind of mounds.
Yeah.
They're little helix.
Yeah.
And if you look at it with a hand lens, they're actually pseudo-triangular. So they look like a little round mound, but they're actually three curved surfaces with three lines coming down from the central point, because quartz belongs to the trigonal crystal system.
Sure.
Small metal plate with one or two holes in dividing the upper and the lower halves to allow the nutrient to travel through. And the aqueous solution is usually an alkali metal hydroxide, which is added to the autoclave. The autoclave is sealed and the whole thing is heated to between 300 and 400 degrees Celsius. It must be less than that 570 degrees because they don't want to induce any twinning in the crystals. And the temperature is controlled so that it has a temperature gradient, so that it's hotter down the bottom and cooler at the top. And that way, as the nutrients rise, the material becomes supersaturated, and then you get the crystal growth happening because of precipitation. So nutrient precipitates onto the seed crystals. With these synthetic materials, the color is going to be very consistent. There's no banding, there's no phantoms. It is very rare to get liquid inclusions in the quartz, but you can get liquid inclusions forming in hydrothermal material. The quartz crystals very rarely have any healed fractures, but hydrothermal emerald crystals quite frequently will have healed fractures that are liquid filled and can look a lot like natural material. You can get other inclusions. We look for something called breadcrumb inclusions, which are tiny, tiny, irregular shaped colorless material that's scattered throughout the crystal that is unlike material that you see in the natural material, unlike inclusions in the natural. But it is rare to find breadcrumb inclusions in quartz. It's rare to find liquid inclusions in quartz. Sometimes you'll find something called a spicule, which is kind of like a needle, a pointed kind of tapered needle. They are often orientated perpendicular to the seed crystal. And in that tumbled crystal that's going around, we had one of the tumbled ones in the collection has a couple of spicules standing up on the seed plate. I'm not sure if it's the one going around though. This is an example of a synthetic quartz that was grown by a lab in America, and they were practicing, of all things, trying to grow twinned quartz crystals. So this was a twinned quartz crystal that they grew, but this was more like a Japan law twin. It isn't actually Japan law, it's a different angle, but it's not the Dauphiné or the Brazil law twinning. This here is an example of a hydrothermally grown aquamarine crystal. It is part of the larger crystal, which I'm going to grab from Adele. Ametrine, sorry.
Different to my understanding.
Ametrine. So that is actually cut from one of these crystals. That crystal is there, this crystal is here. They haven't actually been cut from this crystal, but the one on the screen is the example of the crystal that's going around. From this crystal, it's also got the metal. You can see the metal with the hand lens. Oh, there it is there. You can, this one's sticking out. Yeah, this one is too. I can hold it by the metal at the top of this crystal. It's got the seed plate through the center of the crystal. This would be cut perpendicular to the seed plate to give about 20 slices of ametrine that would then be cut for stones. First, they remove the seed plate, which is this colorless strip through the center, which gives them 2 pieces of faceting rough, and then they can cut the stones into maybe a 50-50, or they can sometimes cut it so that you get a triangular segment of the citrine in with the amethyst sector. And we have some of those in the collection too, just because I think they're fun. Interestingly though, the direction of the C-axis is 90 degrees orientation to what you would expect in the natural. So when you have a slice of natural ametrine, when you look down the optic axis, if the slice is perpendicular to the optic axis, you have the nice segments of the amethyst and citrine, with the optic axis being parallel to the division of colors between the amethyst and the citrine. In the synthetic material, the optic axis is perpendicular to the division of colors, not parallel to the division of colors, which can make finding the optic axes in a piece of synthetic that's been cut for a 50-50 split a little bit tricky. But the fact you can't find the optic axes in a direction parallel to that division of colors is also indicative of the material being synthetic. So you will have opportunity over the next 18 months to play around with that in the lab and seeing if you can find the optic axes. This is another example of a synthetic quartz crystal with an unusual habit, because this has got an almost triangular shape to it, different from the blue piece that's going around. And these are 2 examples of synthetic quartz. These are both very large stones, both bought on eBay as natural quartz, obviously. The one on the left with the seed plate through the center, which you can even see the little triangular growth helix, the little undulating surface there. This was sold as natural ametrine with a certificate saying that it was natural ametrine. Yellow and colorless, sure, yeah, let's call it ametrine. And natural, yeah, no. And the one on the left-hand side, right-hand side, very consistent in color, a bullseye with the conoscope, no color bands, no color zones, and it does have a little few scattered breadcrumbs in it as well. And I'm fairly confident that that one is also synthetic. Okay, on to agates for the last 20 minutes. So we've got the chalcedonies and the jaspers that we're going to do a quick run through. Chalcedony, agates, and jaspers are all varieties of quartz, just with a different structure. So they're not full single crystals, but they're aggregates. The chalcedonies and the agates are an aggregate of fibers, and the jasper is an aggregate of grains. So the aggregate of grains in the jasper makes the jaspers opaque, and the aggregate of fibers in the chalcedony make them translucent to light. Chalcedony and agates are essentially the same material. The main distinction is chalcedonies are usually a single colour and agates are usually banded. But gemology being what gemology is, there's usually exceptions to that rule as well, where we get some agates that don't show any banding, like moss agate. So we'll come and deal with those as we come across them. Okay, so a little bit of jargon from geology, a little bit. So chalcedony is deposited at relatively low temperatures by circulating groundwaters or by magmatic waters that have dropped to temperatures approaching those at the Earth's surface. So the temperature decreases. I mentioned earlier that the hydrothermal process for growing synthetic crystals mirrors what happens in the Earth. And we have temperature gradients that, as the liquids cool down, become supersaturated and then deposit the nutrients that then grow as crystals. So can you see here we have circulating groundwaters, which are initially hot, so hydrothermal, the temperature drops, and then we have deposition of materials that then forms gemstone materials. So as the temperature approaches those close to the Earth's surface, the silica that was circulating in the groundwaters becomes supersaturated, which means that it can't be sustained by the liquid anymore. So it comes out of solution, out of the liquid, and starts to form gemstone material. So the chalcedony and other forms of quartz can be deposited along the linings of fractures or cavities through that process as the liquids cool and the material starts to grow crystals. So chalcedony is a form of silica, and it consists of submicroscopic fibrous crystals of quartz. So an aggregate of fibers of tiny, tiny, tiny little crystals that are too small to see with a standard microscope. It's embedded in amorphous hydrated form of silica, which in another name is referred to as opal. So it's kind of related to opal, these chalcedonies. The quartz fibers may be in layers, so we get a banded structure, and each layer consists of crystals that are orientated parallel to each other with the C-axis at right angles to each layer. So we get a layered banded material. Now, because all of these chalcedonies are an aggregate of fibers, even though they're orientated, the crystals are orientated perpendicular to the layering, we end up with the way in which it transmits light between cross polars results in material that is bright through 360 degrees. So optically, they're not all perfectly aligned to show the light-dark reaction. And in any particular orientation on the polariscope, there'll be enough crystals transmitting light in the on position rather than the dark position. So we always see the light. Chalcedony will occur as a filling in cavities or veins, so in cracks within existing rocks, and may also form nodules or masses. And those masses may show a botryoidal type habit, so we get that undulating surface. This is where we can get those banded structures from. And sometimes they can grow as stalactites or reniform structures as well. And we've got an example of a slice of stalactite quartz in the lab in the cabinet. It's really quite interesting because it's got the crystals growing outwards from the direction of growth, and the color changes to the inside core. That stalactite's actually a form of amethyst. Amethyst, that was the right. I was thinking in my head aquamarine. Don't say aquamarine. It's a form of amethyst, but you can also get chalcedony forming stalactites as well. Chalcedony usually consists of material that is only one color, but where it is banded and with multiple colors, we call it agate, but it's the same material. So the name chalcedony or the name agate is just a choice depending upon the color appearance of the material that we're dealing with. Now, some of the important names that we need to know, one of the most important is chrysoprase. Chrysoprase is the green variety of chalcedony, and it's colored green by nickel. It's naturally occurring, and one of the best locations for it is in Queensland in Australia. The good material is really hard to get these days, but the best material of chrysoprase was often either sold as jade or can easily be confused with jade. But it's really, really nice material from Maryborough. The material can be imitated by dyeing the material. I mentioned earlier when we were talking about dyes that agates are porous and readily take on dyes. So chalcedonies can be dyed very easily, and if you use chromium salts, they can take on a really nice, attractive green color, and that can be sold in the market as chrysoprase. If chromium has been used to dye the material, chromium is pink under the Chelsea filter, so a Chelsea filter may help you identify a treated chrysoprase material. It can't actually be called chrysoprase if it has been treated, and not all green agates that have been dyed with chromium. So they don't all respond to the Chelsea filter, unfortunately. With the chalcedonies, if there are any pre-existing cracks in the material, you can get color concentrations in the cracks, but most of the material that is cut and polished, because it's so cheap and so easy to treat, it's very economical to cut out any of the areas that's showing any color concentrations. So it's rare to find any material with color concentrations in the market if it's been dyed green to imitate chrysoprase. Our president, Michael Obler, he's in the process of closing down his family business because his sons are in IT and don't want to take over. He's got a lot of this dyed chrysoprase from the 70s and 80s that is all very uniform in colour and unfortunately has not been dyed with chromium, so it does not show pink under the Chelsea filter. And I'm really looking forward to putting that on the UV vis and seeing what's going on, if we can see anything. Cobalt can be used to obtain a blue colour in chalcedony also, which can imitate turquoise. So that's something we can also look out for. Blue colours, especially strongly saturated blue colours in chalcedony, is very rare. The blue chalcedony is more of a muted, almost steely, kind of almost lilac-y type blue. But anything more stronger than that is usually colour treated. And if they use cobalt, that will also show red under the Chelsea filter as well. Apparently chrysoprase will lose its colour when it's heated. There's a book downstairs called the Gemstone Treatments, and that lists some of the ways in which gemstones can be treated, and it says chrysoprase will lose its colour when heated. Soaking the sample in water will restore the colour, apparently. These are not experiments that I have done, so I can't actually verify. Sorry, let's do it. I think this is something that we do need to try. It's interesting, the soaking the sample in water, because chalcedony is porous, so there's no reason why it can't take on water. But it's also interesting because there's a type of opal on the market from Ethiopia called hydrophane opal, and it is porous and it will lose its color when immersed in water. Some of the material actually develops a play of color when it's immersed in water. Just depends on the structure of the material that's being soaked. Carnelian is a flesh red to deep red colour, and the colour is thought to be due to iron, or is due to iron. Generally, most materials, if they are red or brown or a green, unless it's a vibrant red or a vibrant green, the colour is due to iron. Sard is the name given for a yellowish through to a brown coloured chalcedony, and onyx is the name given to a dense black chalcedony. Now, spoiler, onyx is widely used in jewellery, but the majority of the onyx that is used in jewellery is treated to obtain that black colour. And that black colour may not penetrate all the way through the chalcedony. So if it needs to be recut, the centre may be colourless or white. And if it gets broken, you may see that the inside of the stone is a different colour. It's treated by boiling the stone in a sugar solution with sulfuric acid, which is the same process that's done on matrix opal as well, to get a dark black background to imitate lightning ridge opal. So natural onyx is really, really rare. My mentor, who died of cancer during COVID, he was a gemstone cutter who was working in Melbourne doing work for some of the jewellers. If he was needing to cut a piece of onyx specifically for a piece of jewellery, because most of the material is treated, he would instead get black jade from Cowell in South Australia and cut the jade to size, because the jade is tougher and harder wearing and takes a better quality polish. And there's not a lot that you can do to test to tell the difference between onyx and jade. So anyway, he'd always disclosed that he was using the jade rather than the onyx, but he would prefer to cut jade rather than onyx. Sardonyx is layered red, brown and white chalcedony. This material has been used in the past for carving cameos out of agate. So you have the lady's face carved away in the white material, and then against a brown or like a dark red background material. So these layered sardonyxes have been really popular for carving. Praise is a dark bluish or yellowish green material, which can contain actinolite crystals. And plasma, I've never liked the name plasma. Plasma, dark bluish green, contains inclusions of chlorite. And bloodstone is plasma with spots of red or brown jasper. Okay, rainbow quartz and iris quartz. Rainbow quartz is material that has been quenched and not dyed. So the quenching process introduces fractures into the crystal. Those fractures have a thin layer of air, and the air has a different refractive index to the gemstone material. So as the light passes from the gemstone through the fracture with the air and back into the gemstone again, it undergoes a process of constructive and destructive interference, and you get iridescence from that. So rainbow quartz has been treated specifically to introduce iridescence in fractures, making it look all rainbowy. But there are varieties of chalcedony on the market called iris quartz, which through its growth structure has a diffraction grating effect that sets up constructive and destructive interference with an iridescence. So these are usually sold as polished slices of agate. They're very rare to get, but they're really, really pretty. You have to hang them up like in a window and get the sun coming through it to get that diffraction grating effect. But they kind of look a little bit like the back of a CD-ROM kind of thing. Moss agate, a near colourless translucent chalcedony that contains black, green or red dendrites which resemble ferns or moss. Got 5 minutes to go. So these are all examples of different types of chalcedony. On the left-hand side, we have chrysoprase. At the top, we have some rough chrysoprase. And you can see the inconsistency with the colour and the inclusion of the bedrock or ironstone through it. To get a piece of cabochon chrysoprase that doesn't have any of these inclusions in is really, really rare. And this material, I feel like it should be worth more money than it is, but it's very difficult to find good material. Yeah, some other price of jade though.
That's not jade.
It's not jade. It's not jade, but really nice material. On the right-hand side, we have a piece of moss agate, and then we've kind of got the carnelian in the center with an intaglio carved in it. Intaglio is the reverse of a cameo. So a cameo is 3 dimensions in relief. The intaglio, the image is carved into the surface, and then can be used as a seal to use with wax. It can leave a 3-dimensional imprint raised from the surface. Pseudomorphs. A pseudomorph is where one mineral replaces another mineral while retaining the structure of the original mineral. So we see this happening within quartz. We get it with the petrified wood, which is a pseudomorph with jasper, and we get it with tiger's eye, which is a pseudomorph with asbestos fibres in it. A little bit of debate with the tiger's eye, because there is some research that suggests that tiger's eye may not be a pseudomorph as we think it is, but instead undergoes a process via which the asbestos cracks through to shear pressure, and then the quartz comes along and fills in the cracks and basically encapsulates the asbestos fibres while they're retaining the original asbestos fibres. So it might not actually replace the asbestos fibres, it just might, coat the asbestos fibres in quartz. Either way, because of the fibrous nature of tiger's eye, it is safe once it has been cut and polished, but if you are wanting to learn how to cab or cut gemstones, tiger's eye is an example of a material that must always be cut with a lot of water, because if you cut it dry, those fibres can be breathed in and can do a lot of damage to your lungs. So it must always be cut wet. Oh, this is fun. I love this. Agatized shell. So these are from India. These used to be shell, millions of years ago, and the shell has been replaced with quartz. So it now has quartz structure. It's got the specific gravity and the heft of quartz. It's got the hardness of quartz. It feels cold like quartz. It's got these little druzy crystals in it, but it retains the full structure of the shell. They are so cute. So between 50 and 100 million years ago. We've got some of those in the lab because I bought some at the Jamboree earlier this year. Tiger's eye is golden brown. Hawk's eye is the blue. Pseudomorphs of original asbestos which have been altered to quartz, or maybe not. I was wandering around trying to actually find, because there was a little article that I found in the Journal of Gemology a few years ago that just kind of summarized and went, hey, it might not be what we think it is. And then when I tried to go deep diving into it, there are arguments between academics on academic websites. And it's like, wow, that's just a little too high level for me, but they're still debating it. So 2002, a new investigation showed that tiger's eye does not consist of quartz fibres replacing the original structure of chrysotolite, but rather quartz columns, each containing an included crystal of chrysotolite, and it happens during a shear stress and a cracking process. Potentially. So if you want to read a little bit further, Gems in Gemology 2012 was a summary of that article. And then if you want to get onto some of the academic sites, go for your life. From Western Australia, we get tiger's iron, which is layered tiger's eye and hematite. And if you want to see a really good example of this, go to the Melbourne Museum. As you go into the dynamic earth display, there's a huge piece of this, the size of the wall, that you can have your photograph taken in front of. It does say it's tiger's eye, not tiger's iron, from Western Australia, but you can see the hematite layers really, really clearly. And let's leave it here with Jasper, because I feel like you all want to go home. And where are we? We have got a bit to go with Jasper. Summary of treatments, and then inclusions. Look, the inclusion stuff, if you want to go through the inclusions yourself, that's not strictly examinable. This was me getting really excited to share as many inclusion photographs with you as possible. So we might, from next week, just skip into feldspar, because I want to spend the whole lecture on feldspar. Okay. See ya. Any questions? How are you doing online? Kavitha, you have your hand up. Kavitha?
Oh, mistake, sorry.
Do you have a question?
No, thank you.
Okay, perfect. Okay. See you, everyone.
Bye. Who's